Hello everyone, this is RaySpace, and I'm here to talk about future space endeavors and how to plan for them. There have been many different attempts to plot out the future of humans in space, and perhaps none of them has been more complicated than this particular integrated space plan, but I could also mention, for instance, Heinlein's future history, many future histories from different sci-fi authors, or, of course, The Case for Mars by Robert Zubrin, which mainly deals with just Mars, but extrapolates to the rest of the solar system to some extent. But here we have the integrated space plan, which is this, and it is complicated, and it goes all the way down to human interstellar travel. So that it does have that benefit. It has many drawbacks, but let's take a look at the details here. Let me go over to its own description. So 1989, and this from Rockwell International. So Rockwell is the company that was responsible for the space shuttle. Eventually it got purchased by Boeing. And here it says the Rockwell Integrated Space Plan is a very long-range systematic perspective of America's and the Western world's space program. So not everybody else. It's a 100-plus year vision that was created from the integration of numerous NASA long-range studies, and so a lot goes into this particular chart. But we can, with hindsight, because this is now more than 35 years ago, criticize this for various reasons. But at this point, it was post-Challenger, so the space shuttle's luster was a little bit worn off, but still they were optimistic about how the space shuttle would do as far as being a reusable system and bring down the costs of space access. But to a large extent, that was diminishing at this point. At the beginning, everything that is being said about Starship right now with SpaceX was said about the space shuttle, basically. So we see at the top here the critical path and the American space shuttle program being at the very center. Well, of course, Rockwell would say this. It is their system. So the whole deal, the space shuttle formerly was called the Space Transportation System, and this is the Space Transportation Systems Division. But the name of it gave you the idea that it was something that was part of a greater scheme, and that was indeed the case. So we have the space shuttle, an international expendable launch fleet. That's a given. Everybody has their launch systems that are expendable. This is the first generation of reusable spacecraft with the space shuttle, and they were very generous in including Buran. At 1989, I don't think at this time Buran had flown yet. I'll have to check the exact date. I think it flew in 1989, but it only flew once, of course. But there was every expectation that it would work. But then the Soviet Union collapsed. So here we have Voyager 2 encountering Uranus and various other probes. Magellan, Galileo would be launched on the shuttle, and Mars Observer, Lunar Observer. So most of these are solid. Solar sail demonstration, we've had a solar sail demonstration, but it took a lot longer to get there. Centaur deep space capability, we still don't have, I don't think. We haven't had a Centaur stage demonstrated in deep space. So the Centaur stage is a hydrogen-oxygen stage that is, well, currently, a form of it is currently used on the Vulcan rocket. And that's a new form of the Centaur stage. And that's one that's meant to be a little bit more deep space compatible, but we still haven't seen that demonstrated yet. So Centaur deep space missions will be nice, but we haven't gotten to that yet. Saturn Titan Cassini mission did happen. So a lot of this stuff, as far as the probes are concerned, are pretty solid. Phobos sample return mission did not happen yet. The Russians did try it. Comet sample return mission we did do. There was that. So we've gotten pretty far on this line. Venus sample return mission, forget about it. I don't know what they're thinking putting that there. That's hard. Outer planet flyby probes, yeah, sure. No problems. The crude portion, solar powered electric propulsion, we do quite often, but lunar electric cargo vehicle, we have not. Nuclear powered electric propulsion, we really need to do, and I'll get to that. So I have my own plan now. After all, this being in 1989, it really needs an update, doesn't it? So one of the central portions of my updated plan is actually the nuclear electric stuff. And we'll see that once I show the beginnings of my chart. Here, if we take a look at the bubbles, we see human presence in space, extended duration stuff, Mir, and freedom. Basically, I don't know why it says Soviet Space Station freedom. It's supposed to be International Space Station or US Space Station freedom. So, typo. That would eventually become the International Space Station. So, but here it has U.S. International Space Station Project. That wasn't meant to name it International Space Station, but it's just in general. And actually, 1998 is a good. We started building that in 1999, so that's not too far off. SpaceApp was a thing. A lot of this, the question of whether it's really required or not is a good one, but mostly if they have it in in blue, then it is something that they thought was required. And I agree with solar-powered electric propulsion and nuclear-powered electric propulsion being required. Integrated Mars transfer vehicle, well, that's sort of Starship. It's sort of Starship. Using L1 as a spaceport might not be required. Martian cycling spaceship launch. I have two minds about that one. It could be okay, but I don't know if it's required. So whether the International Space Station was required is a good question. Air brake capability for some things, sure. And increasing air brake capability. Fission power generation, we'll see in my own scheme, is super required. NASA's Shuttle C or shuttle-derived heavy lift capability. Well, I think it's safe to say that a huge segment of the space community is now firmly against that ultimately being SLS, the Space Launch System. So that currently is in dire straits at this point, but it's certainly not Shuttle C, but it is a shuttle-derived heavy lift capability. Behind that level is, by the way, this is the return to flight for the shuttle. And then Delta II, Titans, Pegasus out of all things, Japanese H2, etc. they included. And then Ariane 5 is down here. So they threw everything. They even threw in the Hope orbital plane by the Japanese, an American Shuttle 2, a German space plane, and the British Hotel space plane. So that's the single stage to orbit. Hopeful things on this line. I mean, I like this line. I design things on this line a lot. American Shuttle 2 could have been something like Venture Star, but yeah, that has not happened. They were hoping for another shuttle. They were hoping that they would be able to build an extra shuttle, OV-106. So, yep, there's a lot of things in here, but it is a bit overly complicated and has a lot of existing stuff, even at that time existing stuff, like the early launch vehicles and all that, Ariane 3, Ariane 4 and all. But lots of interesting ideas, like external tank-derived platforms and facilities. Oh, if only we could have done some of that. Tethered systems, yes. We could maybe have tested out some sort of tether for artificial gravity. So this is an interesting plan, and I'll try and find a source of it to link in the video description if I can. But yes, it's a fascinating attempt to map out everything. The downside of this is once you get beyond like operational Mars base, it's a little bit thin on the details as it gets closer and closer to large-scale habitation of Mars and human interstellar travel. Interstellar traversing world ships. I mean, how all this part actually works. We have fusion propulsion here somehow. antimatter propulsion here as a side note on a line. So yeah, that down here it's a lot thinner than up top, where they've got a lot more certainty, as you would expect. But my goal, personally, is to figure out the stuff based on where we're at right now. And some things we've done. I mean, of course, Voyager and Mercury Orbiter and stuff like that, Cassini, a lot of this has been done. And whether it was really essential or not, I'll leave to other people. But what are the technologies that we really need to proceed with as far as I'm concerned? Well, I've started working on my own map and I'm looking for inputs. So let's see. So it's a lot simpler right now because I've just started on it. I've taken as a given Artemis or a Chinese lunar launch system. Either way, I've called it Artemis. It's not Starship or one thing or another. It could be Starship. It could be New Glenn. It could be something else, and then whatever Chinese rockets they want to have, and then eventually a Mars-capable Starship and something like the Kasei rocket as an option as well. That's a hydrogen-oxygen rocket, sort of like an upgraded SLS, but this leads to a lunar base that we could use for radiation shielding and then for low gravity health tests, which we will need to do. I think it's very important. And then probably another step in the middle here is testing out our life support. Probably after we get the radiation shielding properly tested, there's probably 1.5 here that I need to insert to talk about how the life support is working out on the surface so that we don't have to worry too much about that. Automated construction on the moon needs to be tested so that we can use it for a Mars base. And after we get a Mars-capable ship or rocket, we will be wanting to do an uncrewed ISRU test. That's in situ resource utilization. That is to use the resources of Mars to make propellant, and that's it. And then automated base setup, and then crewed Mars base down here. Now, that's sort of the mission side of things and the rocket side of things. Whoops. And then we have the ship side of things. So, one way or another, we are going to need a nuclear reactor. We're going to need a good nuclear reactor, and that is because on the moon, in fact, I should probably have a line to the lunar base from this. Let me just see if I can draw a line. There we go. All right. Nope, stay there. So, the reason being that the moon, for 14 days out of every 28 or so, is in the dark. So it can't use solar panels for any long-term base. And so we need a nuclear reactor there so that it can stay powered during the nighttime, which will also be very cold, and so they're going to need heating from the reactor as well. So we need a sufficiently large reactor for that. We also would like a sufficiently large reactor of this scale, 50 kilowatt to 500 kilowatt, for nuclear ion propulsion for decent-sized vessels. So this is xenon or argon, nuclear ion propulsion, and then we can have nuclear ion cargo vessels. And then using those, we can get better base modules for the moon. People might think, oh, well, we can just send everything with Starship. I don't think that's the best way to do it long term. Especially since Starship, efficiency-wise, it's not great and it can't be refueled on the surface of the moon because it's methane. And no, we really can't get carbon very well on the moon. If you want to put another item in here for trying to find carbon on the moon and getting it at the scale that we need for Starship, be my guest, but that's probably pretty far down. So, we would like some other cargo vessel to send stuff over to the moon if possible, and Ion is decently efficient, and so it's probably the best bet to get really heavy loads over to the moon, and then we can have a Starship there. Starship can do the landing. It's just that we don't want to have Starship bring it over all the time. We'll have a Starship parked there. We'll send over the fuel with the Ion, probably, since it needs methane. It would be nice to have a Starship that could be refueled on the moon. That would be hydrogen and oxygen using the water on the moon. If you want to throw that into the mix, that would be fine. Personally, I would. I think I might even make that starship that uses hydrogen and oxygen. So we'll think about that. So we need radiators if we're going to have the nuclear reactor. And we need the nuclear reactor no matter what we do, right? Because the base on the moon is got to be in the dark for 14 days out of every month. And also on Mars, the solar input is half what it is on Earth. So if we're going to run the ISRU units to get propellant, we're most likely going to need not solar panels, but a nuclear reactor. So we need that nuclear reactor, and if we've got a nuclear reactor, we need radiators. And we would like radiators that are better than the current aluminum radiators on the ISS. So that's titanium, niobium, or molybdenum. These niobium and molybdenum were proposed, well, actually, I think might be even tested for the NERVA in the 1960s. So that's not really new radiator technology, neither is titanium, but deploying it in space we haven't done. So, at least as far as I know. So, titanium, niobium, molybdenum radiators, and that will feed into the nuclear ion propulsion, and hopefully we will eventually develop carbon composite radiators, which will be better and more necessary for higher power nuclear reactors. The higher power nuclear reactors will better enable Vasimir, which is a somewhat more efficient style of electric propulsion. And so the more powerful radiators and the more powerful reactors will feed into that. And I mean, it's not strictly necessary for Vasimir, but it's ideal. Ion is very slow. And then if we can eventually get a Vasimir with hydrogen or a nuclear ion with hydrogen through, I don't think we need well, the cargo vessel aspect can feed into this. And then we've got a hydrogen nuclear electric propulsion. It could be either Vasimir or this. And then combine that with a bimodal NTR. Bimodal means that the nuclear thermal propulsion unit, sort of like NERVA, also provides electric power. If your reactor is only doing the nuclear thermal stuff, then you either aren't getting power from it, or you need a really big one to get a lot of thrust, and then you need a lot of radiators. So this is a limited bimodal NTR, 1 kilonewton, which is what you get out of 5 megawatts. So it's a very small engine, but it's still probably 100 to 1,000 times the thrust of either the Vasimir or the nuclear ions, given the same reactor. So the reactor will either power the NTR or it'll power the electric. You'll have a 5 megawatt reactor on the high end here, and that will give you a little bit more thrust on this nuclear engine than you otherwise would have gotten. And so that's another option, and that will enable crewed vessels to some extent. You'll probably still need a boost, but with 1 kilonewton, it's really low. It's really pushing it, but I think I could make it happen. So that's why I've got it like this. Otherwise, you can use a bigger NTR, but then you're going to have to shut it down and you can't get power from it. So that's the idea there. You'll have to have, in that case, have 2 reactors, a big one and a small one. But along the way, we need to be able to store hydrogen. If we're especially going to use hydrogen for Vasimir, or it would be nice to be able to use hydrogen with the electric propulsion in general because it's more efficient. But I mean, that's contingent on having a powerful reactor as well, because otherwise hydrogen doesn't give you much thrust. But if you're going to use hydrogen, you need to have ultimately 0 boil off. And so, but the good thing is you have a powerful reactor in order to make that happen, to allow for the cooling. The downside is we haven't tested it yet. So that's that part of the map. Now, for more advanced stuff, I haven't gotten very far with this. I haven't gotten to, interstellar technology yet, but I think you can see I'm plotting it out in a way that's a little bit more systematic than what they had in the Rockwell version, because we have a little bit more foresight and also a lot more theories since then. So we'll see how this all shapes up. My lines are decently crazy, so it's probably going to get crazier. We're going to need a silica quartz pressure vessel if we eventually want to use a gaseous fission core, that is a nuclear light bulb. You need that, you need advanced neutron and gamma shielding, and you need even better radiators. So I'm going to go with either you're going to have a carbon composite radiator or a liquid droplet radiator to enable nuclear light bulb to happen, the closed cycle gas core. So efficiency-wise, a nuclear light bulb starts off at about 1500 and goes up to 3000. Vasimir can get better than that. The nuclear ion gets about 3000-ish, but with hydrogen can get up to 20,000 potentially. Let's say 10,000 just to be safe. So 10,000 there would just go ahead. Right now, Vasimir is at about 4,000 something, and with the that's with argon. With the hydrogen, it could probably do 10,000. It's just round numbers at this point. This future, so the nuclear light bulb has the benefit of thrust. These have the greater benefit of efficiency, and so this is the map so far. This is my integrated space plan, but I'm gonna propose stuff in the future. If you want to throw in some ideas about how it's all gonna shape up, in the comments, you could just do a little arrow diagram and go this to this to this to this for whatever your favorite sort of system might be to integrate into all this. It is an integrated space plan, so you might as well throw everything at it. As this said, the goal of this chart was not to have a, I was about to say coherent, not to have a simple plan, but to just integrate numerous NASA long-range studies. Well, in the comments, you can try and convince me of some sort of thing that I need to integrate. We are not NASA, what can we say? But maybe we can do something with this. And this is my starting point so far. So, with that, thank you for watching. I hope you enjoyed this video. If you did, please do press like. If you have any comments or suggestions, please leave them in the comment section below. And I'll see you next time.